class. Welcome to the next and last section in chapter 10. This is chapter 10.7, where we will be talking about probability and statistics. So, statistics, in a nutshell, right? Let's talk about that for a second. If we want to know something about an entire population, so this could be something like the number of people in a state, let's say Louisiana, who can speak more than one language, average commute time to work, average lifespan of a metal hawk dragonfly, right? Anything that is a population. So, population is the question of all individuals, items, whatever, that have this a shared property. Okay, so it could be everyone who has to drive to work. It could be everyone who's taking an online class. It could be everyone who lives in an apartment. Um, it can be everyone who drives a certain type of car. It can be, like whatever shared characteristic you want to talk about, that is everything that shares that characteristic is a population. Okay. So the best way to gather the information for a population is to contact every member of that population. Right now, I say member, that doesn't mean necessarily people, because maybe, again, like this metal hawk dragonfly, maybe I'm talking about um, animals, bugs, or inanimate objects, right? Maybe I'm talking about all Ford Focuses that were made in 1999, right? So if I want to find out something about Ford Focuses, um, ideally I would look at every single Ford Focus. Let's say I wanted to know how much a Ford Focus actually weighs. If possible, I would look at every Ford Focus ever made and average out their weights, right? Like that would be the best way for me to get that information is to contact every member of that population that I'm interested in. That's generally impossible, okay? Especially if you're talking about living things, right? Let's say I want to know the average size of a housefly. It would be impossible for me to gather every housefly ever and find out how much it weighs or how big it is or whatever it is that I'm looking at, right? Um, by the time I did collect everything, there would be a whole bunch of new houseflies that have already been born and a whole bunch that have already died when I'm looking for more. So there's no way for me to actually contact every element of a population most of the time, okay? So again, how would I find out how long every metal hawk dragonfly is going to live when it would be impossible for me to catch every metal hawk dragonfly ever, right? So an easier thing to do is to gather a sample, right? So instead of looking at every Ford Focus that was made in 1999, I'll go out and I'll randomly find a certain number of them instead. And the amount that I do find and weigh or whatever it is I'm trying to do for Ford Focuses from 1999 would be my sample. Okay. A good sample has to represent your population. So, for instance, if I am looking at all houseflies that have their left wing smaller than their right wing, it wouldn't make sense for me to include every housefly in that case because then I'm not identifying my population well, it's not representing my population. Okay. In a more technical sense, what that would mean is let's say I wanted to know uh, if people like watching videos of mathematics on YouTube, but the only people that I ask are the people who are subscribed to my channel, right? Or are taking my classes. That wouldn't be a good representation because that's not all the people who watch math videos on YouTube. That's just the people that it's easy for me to contact and get information from. So that wouldn't be representative of the population. It would have some inherent bias because I'm not looking at everybody that looks at um, math videos on YouTube, for instance. So, in order to make sure that a sample is representative, I need to have as much randomness as possible within my sample gathering. Okay, so I'm spending a lot of time right now in the beginning. Normally, sometimes I fly through some of these things. It's because this is very, very important. This idea of a sample being representative and the representation of the population comes through as much randomness as possible. That is the key idea in statistics. If that is not true, then everything in statistics kind of falls apart, right? So that's why I'm kind of talking about this a little bit more than I normally would. Um, Now, randomness is not saying like, oh, I'll just randomly pick whoever I see on my YouTube channel to like send them an email. That's not random. In order to be random, I want to take the human choice out of the situation as much as possible. I should be using computers and technology to randomly generate numbers that I assign to people or to elements of my population so that I am not randomly choosing, right? Because if I randomly choose, I will also have some bias, like, oh, maybe I'm not going to ask that person because they look a little intimidating, or maybe I don't want to ask them because of this reason, or maybe I don't think they're going to respond, so why should I even send it to them? So there's things that will come out from my own personality if I'm choosing who to contact individually, right? So there should be as much um, computers sort of choosing things for me as possible. Okay. So if our sample is representative of the population, which is really what we want, then the information that we gather from using our sample will allow us to do what's called an inference. If I have a good sample, I can say, hey, if my sample is representative of the population and I did a good job randomly selecting the elements and for my sample, then whatever information I get out of my sample I can then apply that to the population, right? And so the opposite of this would be something like a prejudice, where I've had one bad um, interaction with someone from a population, and then from that interaction, I say everybody in that population acts like this, right? And so we're doing the complete opposite of that, is making sure I've contacted enough people from a population randomly in order to say that the amount of contacts that I have should be representative of the whole. Okay. So the random process that I'm interested in varies in value every time I take a sample. So if I'm interested in some sort of a measurement, height, weight, the amount of time you have to wait for something, the age of something, um, every time I take that measurement, it will differ between the elements of my population. And every time I take that measurement, it will differ inside of my sample. Okay. I represent whatever it is I'm trying to figure out that I'm measuring. It's not always a measurement, but I represent it with a variable x. Okay, so just like normal. And again, most of the time, these are things like weight, height, favorite color. It could be number of times I had to blow my nose when I was sick. It could be a million different things, right? Whatever it is I'm interested in. Okay. The probability of taking on the values in the contextual domain. So the contextual domain, if you don't remember, is the domain of values that I plug into my function that actually make sense, right? So for instance, if I say, um, how long does it take for you to wake up after your alarm goes on off in the morning? If that's what I'm interested in and that's what I want to study, negative numbers wouldn't make sense in that case, right? It would just be my alarm goes off, I wake up, right? If I was already awake, I would count that as zero. I wouldn't count that as a negative value. So there's values that make sense for the context of the situation, and that is the values that we allow our function to take on. Okay, and those values are distributed or modeled by some function, which we call f of x. Okay, so this function f of x we call the probability density function, or PDF for short, since statistics and probability have a lot of long names for things. We use a lot of acronyms. Okay, so let's say that this circle represents my population. Okay. Now I want to gather a sample from this population and it needs to be representative of my population. So everything in the sample has been collected randomly, right? And a good sample mirrors the population that it came from. And so once I collect the data from the sample that I collected, where I'm taking my measurements, I'm taking my counts of whatever it is I'm interested in, I then analyze my data, and I can then, from that analysis, make an inference about the population. So whatever information I gather from the sample, if it's a good sample, I can say whatever I got from this is true then about the population, right? So for instance, if I want to know the average lifespan of a meadowhawk dragonfly, I would find several locations where they're known to breed, not just one. I would try to go to several locations where I would think dragonflies are bred. They're generally around water, so I would go to several ponds or several creeks, right? And I would assign those locations a number, right? If I'm looking on a map, I could say, okay, I'm going to label these 1 through 100, whatever, however many bodies of water I'm interested in going to based on their breeding range, right? So then I'm going to use a random number generator to select a few of those numbers that I've given to the locations, right? So um, I would then go and collect some eggs. Once I went to those locations, I would have to go find some eggs. Hopefully, I would find several locations in each location where there are eggs, and I would do the same thing. I would label those locations at each creek with, 1 through whatever number. Use a random number generator to randomly generate, you know, which locations within that certain creek I found to gather eggs. And depending on how many eggs are there, I would do the same thing. I would randomly, label a row of them, or randomly. So if I see that there's 20 of them, I randomly select 3 from each one. So the more randomness that I have, the better my selection is. Okay. So I would then hatch all of those eggs that I gathered, and I would measure the lifespans of those dragonflies that I found. Right. Now, obviously, there's problems with that because when you have things in captivity, they tend to not live as long as they would in the wild. So then you're going to have other problems to come up with that kind of a sample. So ideally, whatever it was that I was looking at, that average lifespan, but that value that I got from my sample, once I did all of that work, I'll call X bar or recall X bar. It should be very, very close in value to the average for the entire population, right? So since I got a good sample, that average lifespan that I got should be very close to the average lifespan of all of the dragonflies because I randomly selected my my selection. Okay. The average for the population we call mu. So it's important that we point this out that X bar and mu both represent average value or mean value, but X bar is the mean value from the sample. Mu is the true mean for the entire population. Okay, so again, this big circle is our population. Okay, from that population, we gather a really, really good sample that's representative of our population. From that sample, we make our measurements, we collect the data from the sample, um, then we analyze that sample and we get the value X bar from that sample, right? The average lifespan out of my sample. And from that, I can then make an educated guess, right? An inference about the actual population average, right? The actual average lifespan of all of the dragonflies. So that's a nutshell of how statistics works, right? Gathering a sample and using that sample to talk about your population. So probability is one of the vehicles that we use to make analysis of our data, right? We can use integrals to calculate the probabilities of any random process. So again, the things that we're measuring, height, weight, um, number of minutes you stay asleep after your snooze goes off, right? All those things that I talked about are random processes, right? And they can be modeled with, if they are modeled by a continuous function, then we can use integrals because it's not always a continuous function, right? We call the variable that is attached to a continuous function a continuous random variable because the function that is applied to that random variable is continuous, right? We can use a continuous function. So examples of some continuous random variables are things that are measured. So anything for continuity is measurements that I'm taking. So things like height, weight, length, distance, speed, etc. The things that are not continuous, which we call discrete random variables, are things that are counted. How many times have I used the restroom? How many times did I eat to get today? What is my favorite color, right? Things that fall into a category, categorical things are discrete, things that I count. Okay. If we have enough of these discrete items, the things that I count rather than the things that I measure, then, so things that are counted, example, so number of chips in a bag, amount of items that are sold in a day, etc., then we consider them as a continuous random variable also. So just to reiterate, if I have a discrete variable, right, something that is counted, right, but if I have a large number of counts, then a large data set of those things can act as a continuous function. So I can approximate large discrete samples with continuous functions, right? So for example, or just an out of, an analogy is if I have a little bit of sand in my hand, I could count the number of grains of sand that I see. Okay. However, if I have a bucket of sand, I can pour it out and it can flow like a liquid, right? Anything that flows would be modeled with a continuous function. So I could take a few grains of sand and count them, or if I have a lot, it can flow like something that is continuous, right? So that's the analogy that I like to use. Okay. So if I have a large sample of discrete items, right, a large sample from a discrete random variable, I can model it with something continuous, with a continuous function, which means then I could take integrals in order to find probabilities. Okay, so we use the probability density function when I want to find probabilities, right? So the probability density function, that PDF, it models the probabilities of that continuous random variable. So that was a lot of sort of front loading. So now we can start to get into the mathematics now that we have a semi-decent understanding of what it is that we're talking about, okay? So for any probability distribution or density function, the total area under the curve is always equal to 1. 1 represents 100%. Remember, probabilities are percentages. So 1 is 100%. So if my function represents probabilities, the entire area under the curve is all of the probabilities possible, or 100% of the items. Okay, 100%. Probabilities of random events, continuous or discrete, cannot have negative values and they cannot be more than 1. 1 is 100%, 0 is a zero chance of something happening, right? So these are the probability values, right? Not the data values themselves, but the probability of one of those data values occurring. Okay. Probability of something happening cannot be negative. The probability of something happening cannot be more than 100% or 1. So my probability distribution function then has to be between 0 and 1 for every x. In fact, most of the time it's much smaller than 1 because um, if it's 1, then you just have a point distribution, which is not very useful for studying. So the integral from negative infinity to infinity of my probability density function is 1, 100% of the probabilities possible. So let's talk about using integrals to find probabilities. So the probability that an event occurs from A to B. So for instance, let's say I'm talking about, again, waking up in the morning after I hit the snooze on my alarm. What's the probability that I sleep from 2 more minutes to 4 more minutes after, right? So if I collected a bunch of data from people, they all gave me different values. So what's the probability that if I were to randomly choose one of those values out of my data set that I collected randomly, that I get a value that's between 2 minutes and 4 minutes, right? That would be an example here. So the probability that my random variable that I'm interested in is between A and B is equal to the integral of A to B of my distribution of probabilities given by this function f of x. Okay, so let's go ahead and do an example. Let our distribution function f of x be some constant over 1 plus x squared. Okay, so for the first part, what value for this constant in the numerator will make my function be a probability density function? So remember, what does it mean to be a probability density function? It means that the complete area under the curve is equal to 1. Okay, so what value of c, if I integrate this from negative infinity to infinity, will give me out a value of 1. So the entire area under the curve has to be 1, right? So the total area from negative infinity to infinity of c over 1 plus x squared with respect to x has to equal 1. And so here, obviously, u substitution won't work very well, but we have some square plus another square, so we would want to use some sort of trig substitution, right? So I believe this is a tan x sort of deal, okay? Um, we split this from a to 0 and 0 to b. Um, Here I'm letting a go to negative infinity and b go to negative infinity because that is what we do, right, when we have a improper integral. So I can't evaluate an infinity, negative infinity. So here we go. We have our bounds from a to b, and I'm splitting it in half at 0 because I need one for the lower limit and one for the upper limit. Okay, so again, this should be tan theta, right? Because the a value is 1. So when I plug in tan theta here and I square it, I will get a Pythagorean identity. And I can plug in secant squared once I do that. So x is tan theta, differentiate both sides, okay? Make my substitution. So 1 plus tan squared dx turns into secant squared theta. Same thing here on the other side. I'm just going to be evaluating at different bounds. That's the only difference between these two, right? So here we know that this is really secant squared. We know this is really secant squared. So those secant squares cancel, and I just get the integral at these bounds of c with respect to theta. So I have c theta from 0 to a, taking the limit as a goes to negative infinity. Here from b to 0, or 0 to b, with the limit as b goes to infinity. Okay, so obviously if I plug in 0 to either of these, it goes away. So this turns into a negative CA or AC. This turns into BC. Here, B goes to infinity. Here, it goes to negative infinity. Okay. Uh, oh, I'm sorry. This is what happens. This is X, so I gotta plug in my X value, which is tan theta. So uh, tan theta, solving for theta, gives tan of X inverse, and then I'll plug in my X values once I have that, right? So we can look at a graph of inverse tan, or we could just try to remember the values, which I never do. We could, make ourselves a triangle so then we can look at those values. Um, but tan inverse at 0, I believe is 0, and this is 0, so those two fall off. So I have a negative tan inverse of A and tan inverse of B. Okay. When I go to negative infinity here and to infinity here, I they go to the same value, except for one is negative, right? So this one is negative, this one is positive, and that value is pi over 2. So this is a negative, negative pi over 2. This is pi over 2. So I got c pi over 2 plus c pi over 2, pi over 2. Half a pi and half a pi is a whole pi, so this is c pi. And I know that all of this that I just did is equal to 1. Okay, so c pi is equal to 1. I solve for c, so then c is 1 over pi. Okay, so if I have the value 1 over pi here, that is what gets me, that's what creates this into a uh, probability density function. So for part B here, we want to know what is the probability that x is between the values -1 and negative, I'm sorry, negative 1 and 5. Okay, so we have now as a probability distribution function, density function, it's 1 over pi. Um, looking for the probability between negative 1 and 1 of 1 over 1 plus x squared. Right? So this 1 over pi now makes it a probability density function. And so it's the same work that I did before. I make this tan theta substitution. Okay. Um, here due to symmetry, I can go from 0 to 1 and just double it. If I didn't want to do that, I could go from negative 1 to 1. That's fine. But whenever we have symmetry, that's always very, very helpful. I know that this turns into 2 over pi, that's c, times theta, and the theta was tan inverse x. I've already done all the work here, basically. So I'm going to plug in 1 and 0. 0 we know goes to nothing. When I plug in 1, I get root 2 over 2. Because it's the 30-degree angle, that gives me the 1. And so, I'm sorry, 45 degrees, right? Because sine over cosine is the same. So that's when I get root 2 over 2. Those 2's cancel, and I just get root 2 over pi. Okay. So the probability from negative 1 to 1 is root 2 over pi. So let's do another example, a different example. This one with context. Okay. So the distribution of heights of adult males in the US can be modeled with the function f of x is 1 over 3 times the square root of 2 pi e, and this is all the exponent here, negative 1 half, and then this being squared, so x minus 70 over 3 squared. Okay, so what is the probability that a randomly selected male in the US is between 72 and 75 inches tall? Right. So we will take this integral from 72 to 75. Okay. So the probability that x is between 72 and 75. So again, this collection here, this population that I'm interested in is adult males in the US and their measured heights, right? So what is the probability that a randomly selected male has a measured height between 72 inches and 75 inches? That is what this statement here mathematically is saying to us in the context of our situation. So in order to find that, I take the integral of my function from 72 to 75. And this is it's a rather difficult integral to find by hand. So this is perfect for using like a Simpsons rule or um, uh, technology, Wolfram Alpha, a table of integrals, right? So we'll just go ahead and tell you that the value here is 0.2047. So as a percentage, the probability that a random adult male from the US is between 72 inches and 75 inches is 20.47%. I have a 20.47% chance of contacting a random adult male and having their height be between 72 and 75 inches. So again, to restate that, 20.47% of adult males in the US are between 6 foot and 6'3", 72 inches, 75 inches. Okay. So this is an example of the normal distribution, right? That previous example, I took it from the normal distribution. I actually looked up the values that we were using here. This is true values. That's a true um, percentage, right? Probability value that we would find for an adult male in the US. So in the previous example, um, the distribution that we used was called the normal distribution. It's called the normal distribution because it happens so commonly, right? So often that it's normal for it to show up somewhere. Okay. So for instance, when I'm looking at those metal hawk lifespans, it would probably be a normal distribution, right? And once I gathered a bunch of data and I started to graph stuff, it would look like the normal distribution. The normal distribution has other names, such as the Gaussian distribution, or more commonly, a bell curve, right? Because it looks like a bell, right? So another name for this distribution is the bell curve or the Gaussian distribution. Um, and the shape of this bell curve changes on two parameters. Those parameters are the average value of the sample, right, or the population, and what's called the standard deviation, which we'll get into later. So the population mean mu and the standard deviation sigma is what uh, sort of tells us the shape of the bell curve. Okay, we're not going to get into how it changes the curve because it's not a probability or statistics course. We're just going over statistics and probability at the moment. Okay, so here you can see that my number line, which we'll talk about later as well, is in terms of sigmas, right? My mu, my average is in the middle, and then I count one standard deviation away and two standard deviations away, three standard deviations away, four, five, etc. Right? These sigmas are my standard deviation. I can also count in the opposite direction by my standard deviation. So let's say my standard deviation was three. So okay, let's come back to this example. The average is 70, okay, which we'll get into, and the standard deviation is three. So for this number line, I would replace this with 70, right? 70 would be right in the middle. The average height of an adult male in the US is 70 inches, and the standard deviation is 3. I would expect to see someone 3 inches taller or 3 inches smaller. So this would be 70, 73, 76, 70, 87, 84. I'm sorry, 64. Going kind of the wrong way, right? So 70, 67, 64. Okay, so under the average, above the average. The distribution is 1 over sigma, okay? The standard deviation, square root of 2 pi, e to the power of negative 1/2, my variable minus the population mean divided by the population standard deviation and squaring the entire term, okay? This entire term right here in the middle has a special value as well, which we call a z-score, okay? We'll kind of sort of get into that at the end also. So now let's talk about average value. We have a video already that we talked about average value, and a lot of the things are very similar here, right? Um, so the elements from average value and the elements, the things that we saw in the center of mass, you'll also see here in the average value. The average value is what we call the mean, right? So that's that x bar and that mu value that we're looking at. So when we're talking about discrete cases, we find the average value of a sample by adding everything up and dividing it by the number of elements that we have, right? So the average, so the sample mean is always x bar, right? So what we do for x bar is we add up all of our data values that we have from our sample, and then we divide them by the number that we have present. So x bar is the sum of all of my x values and then dividing it by the number of values that I gathered. Okay? The larger our sample is, the closer our sample mean is going to approach the mean value for the population. And this should make sense. So we go all the way back up here. Okay? The way this works is I take a population, and in that population, I gather a sample very, very randomly. Okay. Now, if I have a very large sample, it should be very close in size to the population, meaning that the average value I get from the sample will be very close to the population average because my sample is very close to being the same size as the population, right? So the larger my sample is, the closer it should be in value to my, the larger our sample, the closer our sample mean x bar approaches the mean value for the population mu, right? So the limit as my sample gets very large of the average value, okay, which is the limit as n goes to infinity of 1 over n, sum of the x values, is going to be the same as the population. So as my limit, as my sample gets larger and larger and larger and approaches the size of my population, the average value of my sample will approach the value of my mean. Okay. So when we have probability values, we can find the mean by taking the sum of data values multiplied by the probability of occurrence. So it's actually the same thing that we're doing here, but instead of having data values, I have probability values, right? The probability that I sleep for 2 minutes after my alarm goes off is this amount, right? The probability that I'm 70 inches tall is 50% as a male adult in the US, right? So I can find my X bar by adding up the data values and dividing it by n. But if I have probability values, I take my data value and I multiply it times the probability of its occurrence. All right, and I add all of those up, and that will also give me X bar. Let's look at an example. So let's say a very easy example, we have a data set that we call A. Generally, we give a data set a name, so it's easy to distinguish between them. So for this set A, let's say the data values I have are 1, 1, 1, 2, and 3. Okay, very small data set. So since there's 5 values in our data set, each value has an occurrence probability of 1 over 5. Okay, so for me to randomly choose something in there and pick one out, there's a 1 in 5 chance that any of those get chosen, right? So the probability of any of these are occurring is 1 over 5, or 0.2, or 20%, okay? So if I want to find the mean value, then for x bar, what I would do is I would add up all of these values, and I would divide it by n, right? 1 plus 1 plus 1 plus 2 plus 3 divided by 5. And so here, this is 5, this is 3, so that's 8 over 5, or 1.6, okay? That's 1 over 5, or point 0.2, 8 times, right? So point 0.2, point 0.2, point 0.2, point 0.2, point 0.2. So that's 1.6, okay? So that's the average value from these values in this data set, okay? Let's say instead that we use the second formula where I'm taking the data value and I'm multiplying it times its probability of occurrence, and I'm adding all of those together, okay? So 1 occurs 3 times, and it has a probability, each of those 1 times is the probability of point 0.2 occurring, right? Because I got 1, 2, 3, so that's 3.2s. So point 0.2, point 0.2, point 0.2. So there's 3 of them, and the data value itself is 1. So it happens 3 times, times the probability, okay? 2 only shows up once, so 1 of its probability values, okay? Same thing for 3, and there's 1 of its probability values. So if I multiply these all out and I add them together, I get 1.6 as well. Okay. So let's look at the relationship between these two different ways of looking at the same thing. Okay. So most of you probably have not seen this bottom way unless you took in the stats course, right? Most of us generally, when we think of the average value, we just add everything up and divide by the number of stuff we have. Okay. So note that 1 plus 1 plus 1 plus 2 plus 3 over 5 is the same thing as 1/5 plus 1/5 plus 1/5 plus 2/5 plus 3/5. So if I really just kind of broke this single rational expression apart into its pieces, this is what I would have. So notice that this is 1/5 3 times, so point 0.2, point 0.2, point 0.2. Okay, this is 2/5 only once. And this is 3/5 only once. So 3 times its probability of occurring the amount of times it happens. Right? So I got 3 times 1/5 for 1, 2 times 1/5, 3 times 1/5. Okay. Ideally, I would probably put a 1 right here so that it's 1 times the number of times it's occurring, but you guys can see it very, very clear here when we break it apart why it works very well. Okay. So if I extend this to the continuous case, instead of x bar, I'm now looking at mu, because when I'm looking at the continuous case, I'm looking at the distribution function for the population, no longer for the sample mean. And so my average should be mu, and I'm going to get the integral from negative infinity to infinity of x times my probability values. Remember, f of x is your probability density function. So each x value times its probability of occurrence across the entire function from negative infinity to infinity. that will give me the population mean. Okay, so again, f of x is the probability density function. Another name for the mean value is the expected value. It's the value I would expect to get out if I'm looking at a bunch of different probabilities, right? So mean value is more so when I'm looking at data or measurements. Expected value is kind of more overarching, and it tells me the value I would expect to get when I'm looking at an element from my population, right? So mean, the mu, is equal to E of x, where E of x is the expected value. It's the exact same thing. It's a slightly different way of looking at it, slightly different wording, but the expected value is the same as the average. It's the average value of the population. Okay. So now let's get into standard deviation. So standard deviation is a measure of how data values deviate from the average value. Okay, so we have our average value, our mean value, and we're looking at all the data values we collected, and the standard deviation just talks about how that data is spread out around the central average value. Okay. So when discussing the standard deviation in the values of a random variable in a population, we use sigma. When we're talking about a sample, we use S. Okay. So again, we always have a differentiation between our sample and our population because we're always trying to use our sample to talk about my population. So same thing, but different symbols differentiate between the two. So standard deviation really has three common uses. Okay. The first is a measure of variation within our data set. Okay, our data sample, our sample that we created. So we use the standard deviation as a measure of the spread of the data values away from the mean, right? So a larger value for the standard deviation means that the data are spread far apart from the mean. If we have a small value, then that means that all of our data values are close in value to the mean, right? So let's do an example here. Um, this made up data set that I have, 0, 0, 0, 0, 0, 10, 10, 10, 10, 10, right? So I got 0 5 times, I got 10 5 times. The average value is 5, okay? B also has an average value 5, but I have 4 5 times and 6 5 times, right? They both have the same mean value, right? The average value for both of these is 5. However, one of them is more spread out, right? All the data values are farther away from 5 than they are here. Here, all the data values are 5 away. Here, all the data values are 1 away, right? Both have a mean value of 5, but are spread out differently. So one has a larger standard deviation than the other. So the standard deviation for set A is larger in value than the standard deviation for set B. Now, this was a made up example that looks nice, so you can tell the difference, but generally, since data are random, I would have a whole bunch of different values here and a whole bunch of different values here, and it wouldn't be very clear what the mean was and which one was more spread out or not, right? So I have to kind of make up an example so you guys can see why that works. So number two, the second option, which we talked about a little bit, is I rescale my number line into increments of the standard deviation. So we're talking about the average height, right? And we looked at the graph of the bell curve and I said, hey, I would redo this number line so that this was 70, 73, 76, since standard deviation is 3 and the center is 70, and I would have this at 67 and 64. So instead of talking about, you know, 70, 71, 72, 73, 74, counting by ones, I would then now need to count by threes because I'm interested in things that are 3 away, right? That's my marker of importance is 3. So 3 away, 3 away, 3 away, and then 3 away from that, right? Or 3 and then 6 in this case. And so that is another use for the standard deviation is that I remark my number line so that I'm counting by the standard deviation value instead of by ones or whatever, right? So it's kind of similar to like a football field, right? American football. We count by yards instead of feet. right? So if I wanted to go into feet, instead of counting by 1 yard, 2 yard, 3 yard, I would now count by every 3 feet because a yard is basically 3 feet, you know, uh, a little bit more, a little bit more. Um, and so I would go 3 feet, 6 feet, 9 feet, what have you, instead of 1 yard, 2 yards, 3 yards, 4 yards. So that's how that would work, right? Or for instance, if I'm talking about miles instead of kilometers, right? Whatever the conversion rate between those are, my miles and my kilometers would be different. So I would renumber my number line if I now need to talk in terms of miles, if I'm talking in terms of kilometers before. Okay. So the number line is then renumbered using the units of the standard deviation. The distance that a single data value is away from the mean is then measured by how many standard deviations away it is, right? And so this value, the number of standard deviations, we call a z-score. Okay, so if I come back here as an example, so we're talking about here where the average was 70 and I'm counting by threes. I would want to know, so 70, 73, 76. Maybe I want to know how far away is 75. It doesn't land right on that line. How many standard deviations away is 75 from the middle value of 70, right? And so in order to do that, I would do my data value, which would be 75, minus the average value, and then how many of the things that I'm counting up. How many threes is that? So that's what this is. This is actually the z-score. The x minus your mean divided by your standard deviation gives you your z-score, which is how many standard deviations away are you for whatever data value of interest it is that you're talking about. Okay, so z-scores are very important in statistics, especially when we're talking about the normal distribution. So that's why we're discussing them. See, okay, so the distance that a data value is from your mean value is measured in terms of standard deviations once we renumber that number line. And the number of standard deviations away that it is called the z-score or z. Okay, so a z value or z-score is your value minus your mean or x bar, right, divided by your standard deviation. So in a sample, my mean is x bar, my sample is s. In a population, my mean is mu, and my standard deviation is sigma. Okay, so these are very important. There are very important probability rules that are given by standard deviations that we're not going to go into more deeply here. That'll be for a stats class. Um, but those rules, if you are interested in them, are called the Chebyshev and the empirical rules. So those are entirely based on z-scores. We actually make decisions in probability and statistics based on z-scores as looking at an example. Okay, so a random sample of 12-ounce Pepsi cans from a Pepsi plant has a mean volume of 12.19 ounces. So we went to some random Pepsi plant where they produce Pepsi, and we gathered a random sample of 12-ounce cans from that Pepsi plant. Okay, the sample that we gathered has an average volume of 12.19 ounces. So what we did is we gathered a sample randomly, we measured the volume in each can, and then from those volumes we found the average value from our data set. Okay. If a Pepsi can from that sample, right? Let's say I randomly choose a can from my random sample, um, and that can has a z-score of negative 2.63 repeating. Okay. The standard deviation for my sample is 0.11 ounces. So notice, I don't know anything about the Pepsi plant. I don't know the average for the Pepsi plant. I don't know the standard deviation of the ounces being poured into the cans for the Pepsi plant. I don't know nothing. All I know is information from my sample. I collected a random sample of cans from this plant. From that sample, the mean volume of my sample is 12.19 ounces, which again should be close to what I would assume is the true average of 12 ounces. The z-score for a random can from that sample was negative 2.63 repeating. And the standard deviation for my sample is 0.11 ounces. This is how much I would expect to see um, plus or minus from 12.19 ounces in a can. Okay, so how many ounces of Pepsi are in this random can that I gathered from my random sample that had a z-score of negative 2.63 repeating? So a negative z-score means that that can that we chose from our sample is below the mean of our sample, right? That means that the average, that the amount of Pepsi in this can is under 12.19 ounces. Okay. So X bar, because again, it's from a sample, is 12.19. So using this z-score formula, because I'm looking at information from my sample, not from my population, it's going to be my data value of, which is what I'm looking for actually, minus my X bar, which is 12.19. My z-score is given to me, and my standard deviation is also given to me. The only thing I don't know is how much volume is inside of my can that I chose that has this as its z-score. So since I know everything except for one thing, I can solve for that, right? So plugging in my values, z-score is equal to x minus the mean divided by the standard deviation, because the z-score is the number of standard deviations for my data value. Okay, so solving for x now, I multiply both sides by 0.11 and then add 12.19. Okay, so multiply both sides and then add by my sample mean, and I get 11.9 ounces. Now that's pretty close to 12 ounces. That's really close. However, based on the sample that I got, right, 11.9 is a lot lower than what I was getting on average from a random sample. Okay, so the can from my sample is 0.29 ounces away from the sample mean of our sample. So generally, I would consider this as too far below what I would expect to see from my sample, right? Because again, I don't know how much the plant is actually producing on average for each can. I know it should be 12 ounces because they're 12-ounce cans, but that doesn't mean that that's actually how much it's producing. The machines could be tweaked, it could be overproducing, underproducing. And so to get a can like this from a random sample means that I got a bad can, right? Or maybe there's a bad something in my plant that's underfilling my Pepsi colas, right? My cans. So our can is 0.29 ounces away from the mean of our sample, and we would consider this too far below what we would expect to see in our sample, and we would say that something is going wrong, right? So generally, anything that's more than 2 standard deviations away is considered unusual to see, and that should kind of make sense if we come back and look at our graph, right? 'Cause this is drawn to scale. Um, more than, if this whole area is 1, if I go to 2 standard deviations away and I look at what area is left, that's a very small area compared to the whole, meaning this is a small probability of occurrence, right? Anything that's more than 2 standard deviations away out here in the tails is unlikely to occur. So if I do have something um, from my random situation that falls in a data value out here or out here, I have to think that something may have went wrong. Okay, something um, not right is happening in whatever it is that I'm studying. Okay, all right, we are way over here. All right, so okay, last thing for standard deviation is we can use standard deviation as a measure of relative standing. What does that mean? It means that if I take 2 different groups that kind of represent the same thing, I can then compare elements against each other by looking at the respective groups. Okay, so I can compare values in different data sets or different samples. So let's look at an example of this. Okay, it'll probably be the easiest thing to do. Let's say that I have a student in my Calculus 2 course that receives a grade on an exam of 83. Okay, let's say that the class average was 78 on this exam, and the standard deviation of scores for this exam was 1.9. Okay, so this student did better than the average, right? I teach linear algebra very often. Let's say that a student in my linear algebra just took a test as well, and they got a grade of 92 on their exam, and that the class average was 81 with a standard deviation of 5.3. So that means that this class scored higher in general than the Calc 2 class did on their exam, but the Calc 2 students were generally closer, more tight towards the 78 value than linear algebra. Linear algebra was spread out. Okay, they were spread out away from this 81. So there was a big spread of data. There was a lot of low values and a lot of high values, whereas the entire calculus 2 course kind of stayed very, very close in value, okay, to the B range. So which student did better compared to the respective classmates? So the Calc 2 student got 83 compared to the classes 78, with everyone being pretty tight. Okay, this student, the class had a higher average, but bigger spread. Okay, and so he was pretty far away from 81, much more so than 83, but the spread is going to make a difference here, right? So the z-score for the calculus student is going to be his value, his score of 83, minus the class's average divided by the standard deviation, which is going to be 2.6316. So that's positive. So that means it's above the mean and it's more than 2 standard deviations, which is unusual, which means that he did very good compared to his classmates. Okay. The z-score for the linear algebra students is their value of 92 minus the mean divided by the standard deviation for the class, which is 2.055, which is also more than 2 standard deviations away, but not more than the calculus student. So the calculus student did much better compared to his class than the linear algebra student did compared to his class. Okay. So since the Calc 2 student has a larger z-score, they performed better on their exam than the linear algebra student. So let's say that we're given a probability density function for a continuous random variable. We can find the standard deviation, sigma, by using the expected value function, right? So we talked about the average value, we talked about how to find the mean or expected value using an integral. Here, we just got done talking about standard deviation, and so we can also use integration to find the standard deviation. And this integral for standard deviation is dependent on our expected value, or sigma, right? This E of x. So sigma squared, which we call the variance, which I'm not going to get into because again, this is not a stats course, but the variance is the standard deviation squared. Okay, the variance is the expected value of x minus mu squared. Okay, and to find this, we would integrate -infinity to infinity. Remember, the expected value is x times f of x, the integral of x times f of x. Mu, expected value, is x times that probability density function. So if sigma is the expected value of x minus mu squared, everywhere I see x in this formula, I replace it then with x minus mu squared. Okay, and that's why the formula looks like this. Okay, in the expected value formula, I'm plugging in x minus mu squared. So it was x times f of x. My probability density function stays the same, but for the x value, I'm now replacing that with x minus mu squared. Okay. Don't forget, if you're looking for the standard deviation for sigma, once you do this, you got to take the square root so that you can get to sigma. If you forget to take the square root at the end, you're going to have the variance, okay, not the standard deviation. So the sigma squared is called the variance. Just like the standard deviation is a measure of how the data is arranged or distributed away from the mean, the variance is it measures the same distance. It's the measure of the variability within the data set. Okay, or basically how is it spread out. So it's the same thing, um, but it serves a slightly different function for calculations. Okay, we have an alternate form for sigma squared as well. Okay, so sigma squared, we know that mu is e of x, so I can find e of x minus e of x squared, okay, which is kind of weird. But if I work this out, I'm not going to do it here, but if I were to work this out, it would be the same thing as having the expected value of x squared minus the mean squared. That's probably a slightly easier form of trying to find this, especially since you got to find mu anyways, to just go x squared times f of x. It should be very clear here that, especially since this is x squared, that integration by parts would be perfect because no matter what f of x is, you integrate this 3 times and it goes to 0, right? So this would be the thing that you differentiate, and f of x would be the function you integrate unless, for whatever reason, it's easier to do it the other way. Um, or if x squared and f of x go together really well, like f of x is a polynomial, you don't got to do integration by parts, okay? Um, mu squared here, you would find mu by finding the expected value regularly, like we saw previously. Okay, so let's do an example. Show that the expected value of the normal distribution is the same as the mean of the distribution mu. Okay. So again, I just want to reiterate that we have 2 forms for finding sigma squared. We have this form and this form. I'm not going to show you that these 2 things are equivalent. This is actually left for a classwork for you to show that these 2 integrals come to the same result, right? Which is the variance being squared, or the variance. So let's do an example. Show that the expected value of the normal distribution is the same as the mean of the distribution, or mu. Okay, so I know that the expected value, e of x, is mu. Okay, and I know I can find this by taking the integral from -infinity to infinity of x times my probability density function. Okay, my probability density function is the normal distribution, so that's 1 over sigma times square root 2 pi e to the -1/2 z score squared. Okay. Let x minus mu over sigma be z. That's a nice substitution. I wonder why I would choose that. Okay, so if I manipulate this equation, I can solve for x, which is useful because you see I have an x here. So x can be replaced with z sigma plus mu. Okay, the variable here is z because the z score changes as x changes. Mu is a constant, sigma is a constant. It is an inherent characteristic from the population. It does not change because it is that value of the population. So x is a variable, as we know. Z changes as x changes, right? Each value of x has a different z score. So I differentiate both sides. So I got dz and 1 over sigma dx, right? This is dx. U goes away. I get sigma dz. I would like to, I could isolate x and then, replace 1 over sigma dz everywhere. But this actually works pretty nice because I have 1 over sigma dx here all. So I make the substitution, and you can see here for x, we got z sigma plus mu. Okay, I moved this constant to the front. The sigma goes away because dz is dx 1 over sigma, as I said before. E here turns into the -1/2 z squared, right? Because I'm using z and I'm using an x. So I'm just making those substitutions. Okay. Again, I'm going from -infinity to infinity. Um, so the next thing I'm going to do is I'm just going to split this across. Notice here that this is 2 different integrals, right? So I can distribute this to the e to the -1/2 z squared, especially since I'm doing it with respect to z. It would make more sense for me to distribute this e term across and this constant on the outside across as well. So for the first one, this sigma here moves to the numerator position. So I have sigma over square root 2 pi. These are all my constants. I have z and then that e negative 1/2 z squared that got distributed over. And then here I'll have the same thing, 1 over square root 2 pi, but I'll have a mu instead. And I'll keep mu, well, we'll put up to the outside, and then e to the negative 1/2 z squared. Okay. So I'm going to be a little bit lazy here, a little bit hand wavy. Um, once we know that when we have an improper integral, negative bounds at infinity, positive bounds at infinity, I need to split this in half and into two. We'll just kind of informally bypass that. Just know that we're going to be separating this not at 0, but at mu, as we said earlier, right? Um, so in order to integrate this, let's go ahead and make the substitution for w for this negative 1/2 z squared. And for dw, then I'm going to differentiate this. This is dw. This turns into just negative z dz, right? Because this 2 comes down, cancels, turns into a negative 1. So that's nice because I have my z and a dz. However, it should turn negative now for dw, and this is just EW. So this Z and DZ goes away, which is very nice. Here, I don't need to make any substitutions. We're going to kind of just trail this along, and you'll see what happens to it as we keep working. So now this turns to EW, DW. The sign changes because of this negative right here. All right, so it's negative sigma over square root 2 pi. Here, I'm pulling this u down and across because I have 1 over square root 2 pi e to negative 2z z squared. Okay, I'm just going to kind of hold this as it goes. And we're just going to kind of work on this one. Okay. So here, we'll talk about how we separate this because we know we have to, for the improper integral, we need to separate to two different integrals. Again, we'll just be kind of hand wavy here. Here, notice that I re-substitute in for my z. I probably should have just never substituted for it in the beginning anyway, since the next move I'm gonna just kind of unsubstitute it. But it's a nice exercise in our substitutions. So the z comes back to x minus mu over sigma. My dx comes back, which means that the sigma comes back as well. Okay, so really, this last half, I should have never made the z substitution, but I was just kind of trying to keep in line and do everything one at a time, right? So this one, I kind of go back to normal. We're going to use this um, we're just going to use a important property. This is just my normal distribution, okay? It's the exact same thing as the normal distribution. There's nothing different here. I know the area here from negative infinity to infinity is 1. This half is not the same thing, right? I got sigma, I got z sigma plus the mu, but the z here is what's changing things around, this x in the front. So this front part is not the same. However, this mu, this is just 1, okay? So I'm going to take the limit as x goes to infinity of negative sigma over root 2 pi. And I'm going to replace my uh, z as well, okay? All right. So I had negative 1/2 z for w, and for z, I know that was x minus mu sigma. Okay, so here I'm just replacing that. I'm not replacing the dz because I've already integrated, so this sigma doesn't go away or anything weird like that. Here, same thing, the z comes back because I want to evaluate at z goes to infinity, where I guess z equals a, z equals b. Remember, there really should be 4 integrals here. I would split this at infinity. Or I'm sorry, at mu. If I split this at mu, this would be mu minus mu, right? So this would be 0. E to that would just be 1. And I would have this term and this term as constant, and they would cancel each other out, okay? As you can do that on your own on the side, right? So here we're going to move a little bit faster a little bit because there's a lot going on here. But you should be able to follow that relatively easy for this part, right? So if I were to go from negative infinity to mu and mu to infinity for my two places to evaluate this for splitting this in proper integral, that's what would happen. When I plug in the mu, this term would go away, and this term would go away for each respective parts, and I would have just the constant part here. And just this constant part, which would have different signs and would end up getting added together and go to zero also. So that's why I kind of skipped a little bit and I just went from infinity to negative infinity. And then I just said, hey, let's do one of those and the other one, right? So there's a little bit of hand waving motion here because that does not always work in integration, but it worked here because those constants were identical and then they cancel each other out. So I'm just going to look at what happens when I go into infinity and what happens when I go to negative infinity. And for the one that is attached to mu, I know that goes to 1 because the area under the normal distribution is equal to 1. And what I had here times mu was just the normal distribution formula, right? The entire area under the normal distribution. So I get u times 1 because this is an extremely difficult integral to evaluate. So it's nice that we can do a little bit more hand waving and say, hey, I know this is 1, so u times 1. And then here, instead of separating it into 4, I'm going to separate it into 2, where I'm just looking at the two ends and then 1. Okay, so now let's look at these functions. Okay, I got a constant term times a exponential function that goes that is negative, which means it goes to 0. Okay, same thing here. This also goes to 0, right? Because I'm going to square this and it'll be positive, and this is negative. So when I look in the negative direction, right, when these things are, it doesn't even matter because this function goes to 0 for both of those. There we go, which is going to be just this mu left over. Okay, so plugging in large values of x here, it doesn't matter because it gets squared. And as it gets larger and larger in value, uh, these things get smaller and smaller and it goes to 0. So we're left with mu times 1, which is mu. So the expected value of the normal distribution is mu, and that should make sense because again, if we go back here, the expected value, the central value, right? This has the highest probability right here in the center. Mu, the average value, is the most likely value to occur. That's why it's the average. So we just basically verified that with integration. Okay. So the expected value of the normal distribution is. So let's do another example. Let's consider the exponential distribution, which is given by lambda e to the negative lambda times x when x is larger than 0 and everything else is 0. So if I'm 0 for my x value or negative, I just get an output of 0. So this is how we can look at it from negative infinity to infinity, but really just have our function exist sort of where it matters, right? So the exponential distribution, this happens when we need to wait X amount of time for something to happen, okay? So this could be my wait time at a bus stop or a doctor's office or anytime I have to wait, right? The length of battery life or shelf life. How long do I have to wait for this thing to not be good anymore, right? How long until this bottle of salsa that I opened is no longer good in my refrigerator, right? How long until the milk starts smelling bad? How long until, you know what I mean? So how long do I have to wait for something to occur? It could be service time at a restaurant. How long do I have to wait to get served? Shelf life of an item, as I said before. So those are all things that the exponential distribution tends to model. Okay. So let's say that an urgent care facility sees an average of 8.5714 patients in an hour. Now you might say, how do you get 8.5 patients? It's an average. It's not a count. It's an average value, right? Averages can be decimal values. We want to know what the standard deviation for the probability distribution. So in the previous example, we did an expected value. We haven't done the standard deviation yet. So the urgent care, we're given the average value already. This is the mean for the population. It says this urgent care facility always has an average of 8.5714 patients. That's a mu value there. We want to know what the standard deviation for the probability distribution. Again, notice we don't have a sample. So it's not X bar and S. We're talking about mu's and sigmas. Okay, so again, here as you can see, it says, note that we're given the average number of patients in an hour. The exponential distribution is for wait times. So in this case, it would be the time between occurrences of an event. The event is somebody walking in. So this distribution gives us probabilities for how long we have to wait for the next customer, right? The next patient, I should say, really. So if the average is 8.5714 patients in an hour, how many minutes am I waiting for each patient to come in, right? So what I'm going to do is I'm going to take 1 hour, 60 minutes. I'm going to divide it into 8.5714 equal parts. And I get out basically 7 minutes. This 2, 3 repeating is so far away that I don't even have to consider it in my calculations. It's more than um, 4 decimal points. So if this is tens, hundreds, thousands, 10,000s, 100,000s, this is in the 100,000ths of a minute, right? Which is very, very, very small. So this is not something, so I'll just take this as 7 minutes between customers, okay? Um, this gives us an expected value of mu, right? We already know expected value is going to be the average, but I don't know what the average is. Here, the average is 7 minutes, okay? So my average wait time is the integral from negative infinity to infinity, lambda x, right? Because I'm multiplying x times the probabilities of each x. And so when I start to do the math here, I can make, I don't really have to make a substitution. I can just use integration by parts, integrate x twice. I'm sorry, differentiate x twice, integrate this exponential function. So 1, so differentiate once, differentiate twice, and now I have my integral, right? I just throw all my pieces together. Negative 1 over lambda x e to negative lambda x, and negative 1 over lambda squared e to the lambda x, and that's it, right? I'm going to evaluate at 0 and the limit as we go to infinity. Again, here I'm just kind of being lazy with the notation. So this lambda is on the constant on the outside. When I distribute it in, here it cancels, okay, and becomes negative. And then here I get just 1, okay. And as you can see, I also pulled out a negative. I got a negative and a negative, so I pulled it out to the front. So everything on the inside of the limit is positive. When I plug in 0 here, this turns into 1, and this turns into 0. And so then I got lambda over lambda squared. So this just gives me a constant term of 1 over lambda. Okay, right? And that's coming from here, right? When I plug this into 0. Okay, and recall that it's positive because I'm subtracting this negative value. So I got positive 1 over lambda e naught, or e to the 0, which is just 1. So this is 1 over lambda. So here, I'm going to pull out this e to the negative lambda x that's everywhere to the outside. Okay. And okay, let's add this back in. Okay. And so let's notice that when I'm looking at the limit, okay, this is going to just get very, very large. And this is just a constant. So this whole thing goes to infinity. However, this goes to 0 because as I plug in very large values here, I get very, very small values out for e to the negative very large values. Okay. This is a linear function. This is an exponential function. That means this decreases way faster than this one does. So the whole thing goes to 0 faster than it goes to infinity. So this is 0. Okay. So this limit is 0, which leaves me with just 1 over lambda. So 1 over lambda is my expected value, which I know is equal to 7, right? Because it's 7 minutes between, on average, between patients. So 7 is equal to 1 over lambda, which means that lambda is 1 over 7, which means for my distribution, I now have a closed form for my model. I no longer have lambdas everywhere. I now have 1 over 7s. So in order to find my sigma squared, I'm going to basically do this again. E to the x squared instead this time, minus mu squared, which is 1 over 7. So 1 over 7 squared, or 1 over 49. And so let's go ahead and do this. So if you notice it looks different now, that's because I know what my value is for lambda, right? So this is 1 over 7e to the negative 1 over 7x. So now when I find the expected value for x squared, it's 1 over 7e to the negative 1 over 7x. And this x squared goes where I had just x last time for the expected value. And I'm going to subtract mu squared. Um, in this case, I know mu is the same thing as 7. Okay. So I'm going to do my integration by parts. X squared will get differentiated. E to negative 1 over 7x will get integrated. So remember, this turns into the reciprocal. So this goes to negative 2x. The next one will just be 2. This one will be positive 49e to the negative 1 over 7. Or, hey, look, it's 7 twice, right? Here, 2 will go to 0. And then this one will get a cubed per 7, right? So I'm just being lazy here. And instead of pulling out my calculator and trying to figure out the values, I'm just going to keep it in its generalized form, which is nice because now when I put this integral together, right, I get the negative 7 x squared e to negative 7x. Here, negative 2 times 7 squared x and the e term. Here is a positive times a negative, so that's negative 2 times 7 cubed and the e term. I evaluate this at infinity and 0. Um, at 0, this goes away. At 0, this goes away. At 0, the e goes away, but I still have, again, zeros on the bottom, so it'll be a positive 1/7 times 2 to the 7 cubed. At infinity, I'll just look at what all these do as I plug in large numbers. As we saw before, the exponential term goes to 0 way faster than a constant uh, line or quadratic, right? So when I plug in infinity here, when I look at the limit as it goes to infinity, all of these things are going to go to 0. Um, and I'm going to be left with what happens when I subtract me plugging in 0, and then this negative 7 squared, right, from the mu term. So for the limit, as x goes to infinity, I pulled out the negative, okay? I pulled out the exponential term, and I left all the other stuff in the middle. I did distribute this 1/7, right? That's why there's no term here. That's why the 7 squared is now just a 7. And the 7 cubed is the 7 squared. So I just reduce everything by a factor of 7. I already know the exponential term goes to 0 way faster than the exponential, I'm sorry, than the quadratic goes to infinity. And then what I'm left with here from the 0 is a positive to 1 over 7 and 7 cubed, give me 7 squared. And then I subtract this 7 squared, okay? So this whole thing goes to 0, and I'm left with just these two things, 2 to the 7 squared minus 7 squared. And hey, I got a common factor of 7 squared. So if I pull that out, 2 minus 1 and 7 squared. Well, 2 minus 1 is just 1, times 7 squared is 49. Okay, so sigma squared is 7 squared, or 49. But I want the standard deviation, so when I square root both, I get 7. So for me, it made more sense not to ever multiply out 7 cubed, 7 squared, whatever, because I needed the root anyways. Okay, there we go. That's our example. I know this was a long video. Statistics and probability is an entire course, as well as biology and econ and physics in the previous ones. But that's the end of our applications, right? So for the next chapter, we will talk about polar, we're going to talk about um, differential equations. Okay, so it's kind of like a preview to my DiffEq course. And then after that, we get into conic sections and uh, coordinates, and then after that we get into series. We get into series, which is a really, really, really long, hard, big topic. Okay, see you guys in the next chapter.